We have Eliisa Lotsari from the Department of Built Environment, Aalto University from Finland. And the topic is seasonally ice-covered rivers, their morphology and sediment transport. So the floor is yours.
Thank you very much. So the topic is the seasonally ice-covered rivers and their morphology and sediment transport conditions. So this is based on 4 different studies, what I have been recently published, or which is under publishing at the moment. So this is kind of a compilation of different research what I have been recently doing. As a background, is that the climatic change has been projected to affect the hydrology and the ice-covered flow period and also river morphology a lot in these northern high latitude regions where also Finland is belonging. And so also how these changes in the winter regime affect on the sediment transport conditions and bank erosion processes and magnitudes. So there is concerns growing that how this climatic change might cause these changes in this geomorphology of the river channels, and if it could also mobilize these sediments, which include also carbon and also some harmful substances in some occasions. So for understanding the impacts of these expected changes in the winter period or the ice-covered flow period, it's needed to understand the present sediment transport conditions more in detail in these high latitude northern rivers to fully understand then what could the changes in future be. So the aims, what I'm here presenting, have been to investigate first of all the impacts of these different years, hydroclimatically different years on this river ice development in a subarctic meandering river. Then also to define the impacts on ice cover on these flow characteristics and sediment transport potential, and how these different years affect on the bank and point bar morphodynamics, and how these what are the driving processes of this bank erosion during different parts of the open channel flow period. So kind of to analyze the full year from ice-covered conditions to the open channel conditions and what kind of impacts with different agents are doing on the river channel within this subarctic river system. So this is based on 4 papers. The first aim relates to the paper published in 2019. The second one is under review at the moment. And third is actually a few years ago in 2014 about this annual bank and point bar morphodynamics. And then the aim 4 relates to the 2020 published paper of this bank erosion dynamics. So if interested, feel free to Google and find this paper and read more in detail. But here is kind of a summarization of based on these 4 papers. So the study site is called Pulmanki River, and here you can see on a map that it's on the northern part of Finland, on a border between Finland and Norway. And it's a meandering river which is flowing towards the north. And if you see my cursor, so there's 2 locations in this river reach which we have been detecting in more detail. First of all, this bank location in the down part of the image, and then this cross-sectional analysis site of ice and flow conditions in this one symmetrical meander bend. Also, the whole reach has been detected in the open channel conditions analysis. So regarding the results, so we did, I don't actually see my notes at all in the screen. It's how, oh, now do you still only see the full screen in your screen, or?
No, we are seeing now the presenter mode, so you should try to share the other screen where you have the full screen presentation. Yeah, like this.
Yeah, I was just wondering how to see the presenter notes, which I would need, but anyway, yeah. So anyway, regarding the ice cover development, we did this analysis of this ice cover development based on a few of the equations. So on the top, there is this Stefan equation for analyzing how well the equations are at the moment creating the ice cover thickness details if used on the present data sets. So here is on top how much the ice thickness has been calculated to be in different years in this study site based on the Stefan's equations and accumulated freezing degree days, which is the AFDD. On the lower part, there is also the measured maximum ice thicknesses on these white columns, and then the Stefan ice thickness equation result on this gray column, and compared how much these do match with the actual observed maximum ice thicknesses. Then also there is another Stefan equation calculated only until the March time and not the full season. It's in the striped column, and then there's the freeze thaw days and also the average snow depth depicted here. So there is a lowering line in this maximum ice thickness in this Pulmanki river reach, and it's analyzed how well actually these ice cover development equations can at the moment represent the observed conditions. So there is variation between the years, but best seems to be matching with the 2016 and 2017 year with the observed and calculated ice thicknesses. Then we also calculated how well these equations are matching with the decay time, so the ice decay in the rivers, if it's forecast well or not. And it was noted that we use this BAO equation for calculating based on the maximum ice thickness, where the calculations had been started from the winter, and then also the accumulated thawing degree days used for the equation. So it was noted that on 2017, the calculated and observed ice clearance day matched exactly based on the equations and observations. But on the other days, it has been overestimation in the time when the ice left from the rivers. Also in this beginning of ice melting, which was also calculated based on the average ice thickness and these accumulated thawing degree days, the best match was in 2017, but other times showed overestimation. So why is that? I can't see. So the equations were the most accurate in this winter 2016 and 17, which was shown in the table and figure before. So that year, the maximum midwinter snow thickness values was high, and then the number of freeze thaw days was the closest to the long-term average of this northern Scandinavia, and the rate of thermal snowmelt in the subsequent spring was low. So these conditions were the kind of best ones which the equations were able to forecast. So before being able to analyze how the changes in ice cover are affecting on the river flow and then also morphology of the rivers, it would be important to be able to forecast for the future how actually the ice cover season is developing. So if using these equations for the future, it would be needed to be adjusted so that it would handle the shorter winters, less snow formation, and increased frequency of temperatures, which are crossing the 0 degree freezing temperature. limit. Sorry, I'm hearing some music. Okay, thank you. So for the results of 2, so despite at the moment there is this ice-covered conditions in this river, and the equations are in these ideal conditions predicting the ice cover thickness and also the decay times of the ice cover well. There is sediment transport throughout the whole year. So in the recent study of ours, it was possible to show that the critical shear velocities of these midwinter conditions are exceeded each winter when we detected from 2016 to 21, and the bed load transport occurred there based on the measurements, mechanical measurements, and also calculated bed capture rates. And also it was noted that the confinement by the river ice cover, which is called bottom fast ice, explained the velocity variation and also where the highest flows for the sediment transport occurred in the winter conditions. So this is important as in many studies, if you are detecting the future, the winter period has not been included in such a detail there, and the sediment transport analysis have often concerned only the open channel conditions. But in this riverside, there is continuous sediment transport in all of the years and throughout the year, which could also affect on the Arctic seas, and what the substances are also included within the transport of the sediment. And it was noted based on these analyses that the near-bed velocities, which are causing also the transport, were high at the upstream section. So it's the cross-section 1, CS1 is the upstream, and CS4 is the downstream cross-section. There was yearly variation. So, for example, the yellow dots are depicting a situation where the flow velocity was very low. But overall, the lowest velocities were downstream side of the apex of the meander bend. So there was this spatial variation within the meander bends about these sediment transport possibilities. So the first paper showed that there is changes in ice cover length and how well the ice cover thickness and its decay are possible to predict. The second paper showed that there is continuous sediment transport throughout the winters. And the third paper is concerned on this, how well the open channel conditions, where the highest erosion and impacts on the morphology are taking place in this river channel when the ice has already gone from the river. So the detailed topographical and hydrological data analysis of ours revealed that the magnitude and duration of the spring water stage B controlled the magnitudes and locations of these changes within the meandering river. So the greater the magnitude and duration of the spring water stage peak, the greater the erosion occurring at the unvegetated banks, but the greater the deposition on top of the point bars was. So the short-term spatial evolution of this river was independent from the association with the neighboring upstream and downstream meander bends, but overall to the hydrological conditions of each year during the open channel period. So this is the channel what was analyzed between 2009 to 2012. Sorry, this is a little bit earlier study, but covered a variety of different years. So I'm next showing a more detailed about this bend 6, what is happening there. So this is the river banks based on the laser scanning data set, mobile laser scanning data, what you can see here behind.
Again.
And sorry?
Please go on.
Please go on.
Okay, yeah. So there is in this bend number 6, for example, if detecting in more detail what happened on top of the point bar on that section. So there is on these green colors are showing that there is deposition on the point bar, and yellow colors are that there is erosion between couple of or 2 years, 2 consecutive years. What can be seen that there is on this first year analyzed there is deposition on point bar. Next year there is more erosion on the rim area of the point bar, and then the final year there is more erosion on top of the point bar, and then deposition by the rim of the point bar. So the water is here. So this is the above water area, what is seen from the laser scanning data sets, and it changes. So this can be explained that in year 2010, it had the highest spring flow peak, which reached the point bar, and it lasted also a long time for being able to cause the sedimentation on top of the point bar. But then on 2011 spring, here it had the lowest flow, which is the solid gray line in this graph. And it didn't reach the whole point bar, but caused more on the erosion. So there was no possibility for deposition on top of the point bar. And finally, the 2012 flow peak was a little bit milder than the 2010 discharge peak, but was able to scar the top of the point bar and caused sedimentation on a lower stages of the flood hydrograph. So this happened in all of the point bars, what was analyzed, and showing that the more important for the evolution was the actual hydrological conditions than the different shape or curvature of the meander bends. And in the paper 4, this is the final one, it was analyzed on the same river, this riverbank erosion, if the previous one was more about the point bar development. So what happens on the outer bank side of the bends? This is a high 90-meter high riverbank with different fluvial and lacustrine material, which has been compiled there since the last declassiation. So the annual variation of the high water in the open channel conditions can be seen from the striped mark, which is about 2 meters higher in the spring flow than in the low autumn flow or in the winter flow. So this 15.35 meter above sea level is the kind of a typical ice level and low water period flow mark. It was analyzed based on the topographical datasets, the laser scanned data, acoustic Doppler velocimeter datasets, and also sedimentological datasets, what's happening in this riverbank. So we were able to point out different locations during a one open channel condition year, what was going on. So in the number 1, there is this groundwater causing the effect, which is seeping through the riverbank. So there is one hotspot of this erosion, which is not caused by the flowing water, but the water coming through the riverbank. Then in the number 2, which is in the apex of this meander bend, so the flow is going from, well, you see the flow direction, which is from lower of the picture to the top of the picture. So the flowing water and mass movement during the shifting of the water level is causing this erosion in the middle part of the bend. And there was also throughout the bend erosion caused by the rain and also changes in the saturation and cohesion during the wetting and drying of the open channel period. But what was able to conclude from the analysis that the overall most of the bank erosion and deposition were observed during the low flow period after the spring flood. So also in this case, it was not only the spring flood peak which caused the changes within the riverbank. So we wanted to highlight that despite the spring flow peak might be the highest single event in a year in the subarctic, environment, it might not be the total, or the other times and processes are causing also a lot of erosion in this environment. So in this graph, it can be compared that during the spring snowmelt discharge event, during the peak there was most frequent changes, but in the summer discharge event, the most frequent changes occurred in the beginning of the summer rain-induced flood peaks. And this was concluded that in the springtime, the riverbanks are
2 more
also,
minutes.
thank you, are also mostly frozen still, and therefore there's no yet sediment available for this erosion during the spring snowmelt discharge peak. But during the summer discharge, even the riverbanks are already defrosted, so there is more sediment already available for the transport during those times. So the more knowing about the environment, the more complex it is. So in this type of a system, there is sediment transport throughout the year to the downstream water bodies. And what I wanted to point out that all of the seasons are important for the sediment transport and morphology of the river. And these should be taken into account when doing this future analysis of the changing winter conditions and how much sediment is transported to the Arctic seas. So, and especially in a larger river systems, these would be important to also include, if just possible, for the analysis in these high Arctic areas. So thank you.
Very much for a very interesting presentation and moving us a bit to the north.
Yeah.
I think
Sorry
we
for
have
the technical problems. Yeah.
okay. It's common. It always happens.
Yeah.
I think we can have maybe a short question since we have one more presentation before we go to the break. So if there is a question, you can also use the chat or you can speak if you would like. Okay, I have a short question for you regarding the, if I understood correctly, you did the measurements for the sediment accumulation or erosion based on laser scan measurements, laser scanner.
Yeah, we have used the laser scanner for the bank erosion and also for the point bar analysis. But in the ice covered conditions, we have used echo sounder and then also to get the topography and also the mechanical measurements of the actual transport. And we have also from the summertime period also as a reference data, the mechanical bed load transport data available.
So you did your measurements 2 times per year, because I understand that you have measurements throughout some years, but what was your period of repetition, let's say, of the measurements?
Yeah, we are doing those. Normally, we have been going there in the spring flood time, being there for a week or so and continuously repeat the measurements during the flood times, and then place the sensors to the river for the whole summer, and then going back in the autumn, which is in September, October, either once or 2 times for 1 to 2 weeks field trips, and then also in midwinter conditions for the ice-covered measurements in February for 1 to 2 weeks. So it's not the full year, but we are placing the sensors there. And also we have game cameras which are tracking the changes, so we can have the video and camera data out of the site to fully see the year. Yeah.
Dario, you have a question?
Yes. Thank you. Thank you so much for your very interesting presentation, Elisa. I have a short question and very small question for you. I was wondering if, considering the high resolution of your data, you could foresee the morphological evolution and the effect of the ongoing climate change in this very sensitive sector, very environment. Could you foresee the behaviors, the future behaviors?
Yeah, the area still there is still harsh winter conditions in this area, but there has been seen that the spring snowmelt flood in some years comes already a bit in advance. But what is forecast there to happen is that the shorter time period for the winter will take place, and then also which is affecting on the ice thickness. So, for example, this year when we were 2 weeks ago in this riverside, there was a lot of water on top of the ice cover, and it looked very different to the previous very harsh winters what we have experienced there. So I would say that there is already slight impact seen, but of course there is annual variation taking place in this site also. So even more longer period analysis are needed. We have been measuring the winter conditions since 2014, so that's how many years? 7 years already, but more is needed to be able to see the full development of the river. But I would say that slight impacts are seen already.
Okay, thank you.
Thank you.
Thank you very much. I think we can try to connect again with Noura Fayyad. Are you with us?
Hello?
Great. We can